Okay, so welcome to section 2.3. We've covered a lot of this stuff before. So if you need more examples or if there's some definitions or terms that I'm glossing over, please, again, look in the book. And if there's ever terms that you are having a hard time finding, the index is a great place for it. So if you, say, missed the spanning set or consistent, you can look in the index where consistent is and it will show you definitions of that in like 2.2, 2.3, and so on. Okay, so the first, a theorem. So if I have a linear system with an augmented matrix, right, AB, right, so where A is a matrix and then B is the column of components on the right side of that little line, right, so that's consistent if and only if B is a linear combination of the columns of A. Right, so if we think about each column of A as a vector, then B is a linear combination of those vectors. Right, so another way of saying that is that B is in the span of the columns of A. Right, so for example, if I have this linear system, x minus y equals 1, x plus y equals 3, right, so that only works, I'm saying that this with the augmented matrix would only work if, right, 1, 3 is a linear combination of these two, right? Which is exactly the same thing as saying it's in the span of these, right? Because span means all the vectors I can get as a linear combination. Right, so again, here you can see the augmented matrix. So this would be A, the columns of A are the vectors, right? B, I can row reduce this, and I end up with 1, 0, 2, 0, 1, 1. Right, so x equals 2, y equals 1, right, which means that this does have a solution. It has a unique solution, but really any solution would make us consistent, right? So again, 2 minus 1, so we can see that it matches here. We can see that it meets the criteria for the linear combination. Okay, and then a little definition to fit in. We've talked a lot about what it means if we span Rn. A set S spans all of Rn, then S is a spanning set. So if you hear spanning set of a space, I'm talking about a set that spans all of that space. And normally we mostly talk about this with regards to real spaces or vector spaces, which we'll get at later. Okay, so some definitions. Again, we've covered most of these before, so I'm going through them kind of fast. This is essentially what we did when we did the getting home activity. A set of vectors is linearly dependent if there are scalars such that c1 v1 plus c2 v2 and so on plus ck vk equals 0, where at least one c is not 0. So in other words, they can't all be 0. At least one of them is not 0. And if the only solution is the trivial solution, which means that all of our coefficients are 0, then we'd say the set of vectors is linearly independent. Right? And trivial because it's like if I make all of my coefficients 0, then sure, 0 adds to 0. So we call that the trivial solution. And so that's the definition of linearly dependent. Again, this relates to the getting home task that we did in class, right? Because this is like using each of my modes of transportation once. Can I get home, which is the same thing as the 0 vector. Now I also said that, right, more intuitively, vectors are linearly dependent if and only if, so this is kind of my shorthand for if and only if, at least one vector can be expressed as a linear combination of the others. Right, so let's kind of think about why these two are the same thing. Talked about it in class, but let's get it out here. All right, so suppose that we have three vectors, v1, v2, and v3, and I'm going to assert they're linearly dependent in R3. Right, so we've got some little space here in R3. And so let's look at, right, so if they're linearly dependent, let's say that V3 is equal to C1V1 plus C2V2. Let's kind of see how we construct that. This isn't a formal proof, it's just kind of an illustration to help build some intuition. But V1, right, goes in this direction, V2 goes in that direction. I can't draw three-dimensionally, but you can imagine that these aren't exactly lying on the plane of the paper. Right, so V3 goes out like so. Right. Now, if V3 is a linear combination of C1V1 and C2V2, I can get to V3 using V1 and V2. Right. In particular, I could say that C1V1 and C2V2 gets me to V3, right? But that also means that I have a linear combination that gets me to 0, right? Because it's like I can follow C1V1, C2V2, and C3V3, and I've completed a circuit, right? And that argument kind of works both ways. It's like if I have a circuit, then I can use, right, these vectors to combine to get this vector. I could use these vectors to make that one, right? And in this case, C3 would just be like -1 based on how I constructed this diagram. But any sort of coefficient works. Okay, let's look at just two other examples of things that we might want to practice. So is a given vector in the span of some other vectors? Right, this should be the kind of thing that once we can harness it is pretty easy to solve, right? So a lot of what we're going to be doing from here on out is recognizing what all these various questions are asking, because as we move forward we need to kind of be automatic because there's so many different situations they could come at us with. So right, what that's really saying is, right, if this is in the span, then there's a linear combination of these two vectors that equals this one. Right, so I could think x times 1, 1, 1 plus y times 0, 1, 1 equals 1, 1, 0. Right, so I'm setting up a linear system like so. That row reduces to this one, and you can kind of see that we are not consistent because I've got 0, 0, 1, right? So no, right? 0x, 0y equals 1. That's not going to be true ever, right? Especially not if we've asserted that x equals 1, y equals 0, then, right? So 1, 1, 0 is not in the span of these because there's no linear combination of these that are going to get me here. And the idea that we want to get comfortable with is that row reducing this matrix, or row reducing rather this matrix, proves that. Okay, and then another example, and this is one that we kind of covered in class. How do I check and see if three vectors are linearly independent? Right. So the way that I'm doing that, remember, to check if something's linearly independent, I essentially kind of perform the same test to see if it's dependent, right? C1 times the vector, so is there a set of these such that they add up to 0? Right, so this is solving the homogeneous system. Right? So this is, right, the augmented matrix that corresponds to this vector equation. And if you think about what happens when I row reduce, right, as I keep adding and subtracting, multiplying and dividing my different rows, nothing's happening to the zeros. So in essence, all I really need to do is to row reduce the coefficient matrix. Right? Remember, this matrix is what we called our coefficient matrix because it's just made out of the coefficients of the system. Right? So it's like C1, 0, C2, -1, C3, and so on. Okay, so as I start row reducing, right, I find that I end up with two vectors. So this is row 2 plus row 1, and then I just multiplied negative row 3. I forgot to write that down here. And you can see that these are going to cancel, right? So depending on what my question's asking me to find, if I'm trying to check and see if these are linearly independent, right? They're not linearly independent because I've got a free variable here, right? So if we put this like zeros back in, if I think about what it is, okay, so C1 is equal to C1 minus C3 is 0, C2 minus C3 is 0. C3 can be anything, right? So there's essentially an infinite number of coefficients that would make this linear combination work. So the only time that we were going to look for, if you think about it, linearly independent would mean that I'm row reducing to this matrix, which is ugly because it's drawn with a mouse, but hopefully we get the idea. All right, so if I'm row reducing to that matrix, then I'm going to have a set of linearly independent vectors. Again, this is really, in this case, talking about an n by n matrix. Right? There's other cases where we talk about, say, an m by n matrix, where you're still checking this, and you're looking for free variables. So the book talks some about that. I don't believe it's in the homework due Tuesday. However, if so, I want to review some of that. And we're going to be doing more work kind of tying these things together on Tuesday. Have a nice weekend, everyone. I will see you on Tuesday.